this lesson, we're going to focus on simplifying non-perfect radical expressions. So far, in solving radicals, we have simplified perfect roots, perfect square root, perfect cube roots, and so forth. But we don't live in a perfect world, and neither are the radicals. Some radicals you try to solve, you will notice that it is not a perfect root. So what you have to do is find the perfect inside of it and take it out, solve it, and whatever it equals, it goes outside in front of the radical, and the non-perfect will remain underneath the symbol. Keep in mind, anytime you're dealing with radicals, the only way you can remove that radical symbol is if the entire thing, when you solve it, if it's a perfect root. If it's not perfect, then you solve the perfect and bring it outside, and whatever is non-perfect, again, you will leave it underneath the symbol. So keep that in mind anytime you are solving radicals in chapter 10. All right, so let's find the perfect inside of the first examples, because the square root of 80. 80 is not a perfect square root, but it does have a perfect inside of it. Now, it shows you in class how you can break a number down into primes and then find all the perfects that are inside that number, and whatever is non-perfect remains. In this case of 80, it has, you always want to find, by the way, the largest perfect square root inside, because yes, 80 does have a perfect fourth root inside of it, but we want the biggest root that it has inside of it, and the biggest root it has is 16, because 16 times 5 is 80. So we can solve that largest perfect root. In this case, it's 16. The square root of 16 is 4. Once you solve it, you can now bring that 4 outside, and you're going to bring it out front. Now 5 is not perfect, so it has to stay underneath the radical symbol. You cannot remove it. So your final answer then would be 4 radical 5. Or you can say 4 square root of 5. Both ways are acceptable. Let's take a look at the second example. 63 is not a perfect square root. However, it does have a perfect inside of it. We want the largest perfect number that's inside there. Well, I know that 9 times 7 is 63. So 9 is your greatest perfect square inside there. So we're going to solve it. The square root of 9 is 3. We can now bring that 3 outside in front. 7 is not perfect, so it has to remain underneath the symbol. So that's going to leave us with an answer of 3 radical 7, or you can say 3 square root of 7. And that is how you would solve radicals that are not perfect. You've got to find the largest perfect root inside of it, solve it, put your answer outside in front. Whatever that's not perfect will remain underneath the symbol. Variables. Now, your variables can also be what is called non-perfect. For example, the square root of a to the 5th power. That's not a perfect square, because remember, square root has an index of 2, and 5 is not divisible by 2. But all you have to do here is go down 1, and it will be divisible by 2. You have 5 A's. But if you go down 1 to 4, 4 would be a number that's divisible by 2. So 4 of those A's are perfect, which means 1A is not perfect. I still have 5 A's, but only 4 of them is perfect. 1 is not perfect, so that 1 is going to have to stay underneath the symbol all by itself. So let's go ahead and solve the perfect part so that we can put it outside in front. The square root of a to the 4th power is what? Yes, a squared. So that's going to leave us with a final answer of a squared radical a, or you can say a squared square root of a. Let's move on to example B. So we have the square root of b to the 9th power. That is not a perfect root because it is not divisible by 2. But all we have to do is go down 1. We have a total of 9 b's. But if we go down 1 to 8 b's, we will have 8 that are perfect, which means 1b is not perfect. And that 1b is going to have to stay underneath the symbol all by itself. Let's solve the perfect and put it outside. What is the square root of b to the 8th power? Remember, all we have to do is divide that exponent by the index of 2, and that's going to leave us with b to the 4th power radical b. Let's move on to the last example. So we have cube root, and our exponent y to the 5th power is not divisible by the index of 3, so that is not a perfect cube root. However, we can make it a perfect cube root. Now going down 1 is not going to help us because y to the 4th power is still not divisible by 3. So we have to go down 2. So once we subtract 2 from that 5, we get 3, which means we can make a perfect cube root of y to the 3rd power. I have a total of 5 y's, so that means 2 of those y's are going to remain underneath the radical symbol because they are not perfect. Which, by the way, when you write it, you can write it with a dot between them or side by side. Both ways signifies that they are being multiplied. And again, I have a total of 5 y's, but only 3 of them is perfect. Let's solve that perfect. The cube root of y to the 3rd power is y. We're going to take that y, put it outside up front, and who has to remain underneath the symbol? Yes, y squared has to remain under the symbol. So that's going to leave me with an answer of y cube root of y squared. And that's how you simplify non-perfect variables. Now let's put everything together we've learned about non-perfects. We have our number and our variable both together. So the square root of 45 y to the 3rd power. It's not perfect, so let's find the perfect inside. Well, I know that 9 times 5 is 45, so in terms of the numerical part, 9 is going to be the perfect. For the variable, it's not perfect either because it's not divisible by the index of 2, so I have to go down 1. The bottom line is I want to, in my mind, organize and get the perfect with the perfect and the non-perfect with the non-perfect. Now, you don't have to write it out the way I did. I do this for the purposes of teaching. But yes, 9 times 5 is 45. I had a total of 3 y's, but only 2 of them is perfect. The 9 of the number is perfect, which means that the non-perfect part you see here in black, it's going to remain underneath the symbol. The perfect part, which I have here represented by the blue, I'm going to solve it and it's going to come outside in front. The square root of 9y squared is 3y, so that's going to leave me with an answer of 3y radical 5y. Let's do the second example. That's square root. Now in this case, the number is a perfect square, but the variable isn't. Because we know the square root of 64 is 8. So 8, yes, it's going to come out of that radical symbol. It's going to be out in front. But let's take a look at our variables. Y to the 9th power. It's not divisible by the index of 2. So that means we have to go down 1, which means we're going to wind up leaving one, which means we're going to leave one variable there underneath the radical symbol. So when you put the perfect with the perfect and non-perfect with the non-perfect, it's going to look like so. Let's go ahead and solve the perfect, and it's going to go outside the square root of 64, y to the 8th power. That's going to give us what? 8y to the 4th power. And 1y is going to remain underneath the symbol, and that will be radical y. Okay, there you have it. Continuing with more examples of simplifying non-perfect radicals. As we've seen in the previous example, 80 is not a perfect square root, but it does have a perfect 16 inside of it. The x is not perfect by itself, so it's going to wind up staying underneath the symbol along with the 5 from the 80. So putting the perfect with the perfect and the non-perfect with the non-perfect, because 16 times 5 is 80, plus you have the x. Let's solve that perfect. The square root of 16 is 4. Once we solve it, remember it goes outside in front, but we already have a number outside in front. Well, when it comes out front, if there's a number outside, you will multiply it with that number that's on the outside. So now 4 times 4 is going to give me 16 outside, radical 5x, and you can't do any more to it because remember 5x is not perfect, so therefore it has to remain underneath the symbol. In the second example, we have a negative in front of it, so remember we're going to solve it as usual, but remember it's going to be negated, so we have to put that negative there. So let's focus on solving for right now. 32 is not perfect, but it does have a perfect inside of it. Let's look at the variables and see if they're perfect. Well, a to the 8th power, that's perfect because that number 8 is divisible by 2. B to the 7th is not perfect, but we can make it perfect by going down 1. So I'm going to go ahead and write it with perfect with the perfect and the non-perfect with the non-perfect. Again, you don't have to separate it this way. I just like to organize it that way when I'm teaching so that you can see that what we're going to wind up doing is solving the perfect and put it on the outside and leaving the non-perfect under the symbol. Now, how did we get 16 and 2? Well, 16 times 2 equals 32. 16 was the biggest perfect inside of 32. So now solving all the perfect part, 16, a to the 8th, b to the 6th, let's solve it, and then it's going to go on the outside, our answer, along with that negative. And 2b will remain underneath the symbol, which gives me an answer of negative 4, a to the 4th power, b cubed, square root of 2b. Last example, here we have cube root. Well, the number part of it is perfect because that's a perfect cube root. The r to the 10th power is not perfect because 10 is not divisible by 3, but we can go down 1. The s to the 12th power, it is perfect because 12 is divisible by 3. So let's go ahead and organize it. Perfect with the perfect, non-perfect with the non-perfect. Now I'm going to go ahead and solve the perfect and put it on the outside. And the only term that's going to be left under the radical symbol is just a single r. So when we solve that, our answer is going to be 5r cubed s to the 4th power cube root of r. And there you have it, simplifying radical expressions. This last one is a challenging one, but no worries, you can do it. You got this. So first of all, let's take a look at this problem. We could, because they are the same root of cube root, we can apply the quotient rule and do the top divided by the bottom. So when we do so, it's going to look like so. And by the way, that 5 is still on the outside where it was. All we did was kind of situated them together. So let's go ahead and proceed with that. 40 divided by 5. And then we're going to use the quotient rule also for the y's, because the y, the bases are the same. Top, take away the bottom. Now you can't do that for the x's because there's no x down below. So when we simplify that, 40 divided by 5 is going to give us 8. We just brought x down because we couldn't apply the quotient rule for that, so that's x to the 5th power. For the y's, we did apply the quotient rule, which is top take away the bottom, 7 take away 1. That's how we got y to 6. Now let's look at trying to simplify this. Let's look at the numerical part. That's 8. The index here is 3, so that is a perfect root. What is the cube root of 8? Yes, the cube root of 8 is 2. How about x and y? Are they perfect cubes? Well, for the x, it's not perfect, but we can go down 2 and make it 3 of them perfect. The y's are perfect because they are divisible by 3. So we can go ahead and put the perfect with the perfect and the non-perfect with the non-perfect. So we can see here that 2x's or x squared is going to remain under the radical symbol. Let's go ahead and find the cube root of the perfect cube root there. Solve it. It goes on the outside with, and it's going to multiply with the 5 that's on the outside. So let's see what came outside was 2x. Y squared came outside. Now we multiply that with 5, and what we get outside now is 10x y squared cube root of x squared. And there you have it. You see, it was not as bad as you thought it was. You did it. Good job.